Okay, so first, these are the rooms that we will have the lab sessions. And these are the time slots that we have for the labs. So the first session will be starting tomorrow. So we'll have the 8 a.m. and 10 a.m. sessions tomorrow. But we didn't have the other Tuesday, Wednesday sessions this week. They will start next week. So yeah, so for those that are assigned to the Friday session, yeah, make sure you are in one of these rooms on Friday. Okay, so you can go to any of these rooms that are listed here. So you can find this on the slides, which will be on the website, but they are also listed on the website on the labs window or labs page. And what else? Yeah, so you can go to any of those rooms. Any other questions about this part? Okay. Okay, so how we will do the grading? So there will be 10 labs in total. You'll have, I think, 11 weeks, if I remember correctly, to complete those 10 labs, and you'll get 30 points in total. So you'll find the lab manuals online shortly before the lab for that week, before the sessions start. You should already know the website. And so for the entire class, you will get 70% of your grade from the exam and 30% from the, sorry, this is only for the labs. So you'll get 70% of your grade from in-class evaluation. So for so during the labs, you'll do an assignment and you'll be graded for that assignment in class. But after the lab session, you'll also have to submit a lab report, which will give you 30% of the remaining credits. Okay, so this is only for the labs, not for the entire lecture. Yeah. So I'm not 100% sure about this part, though. I think we didn't double check this, but I think we didn't change this. So you should be able to use your grades from past years if you have taken this class before. Okay, and then you can go and find your last year's grades from previous year's Moodle page. And for lab reports, I think by mistake I put it here. If you submit your lab report late, you will get 1 point penalty. So for every lab, the report will give you 3 points. If you submit it late, you'll get two points at most. Okay. And for questions, you can either send us an email to this mailing list, but the preferred way is to post your question on Piazza. So please do that so others can also see your questions. So like we don't get like multiple instances of the same question. Okay. Any questions about the logistics? Yes. So you should finish the labs 1 week after they're announced. So let's say you are going to 8 a.m. session on Friday. You will have time to finish that in-class assignment until the end of the session next week. Okay, but for the lab report, you will see the deadline separately. So when we post the assignment, you will see a deadline for the report. Okay. But for the lab assignment, you'll have 1 week to work on. So it's basically two lab sessions. Time to, yes. Yes, you can do that. You can go to another lab, but there should be a convincing reason to do that. So like mostly try to go to the session that you're assigned to, okay? Because like there might not be space for everybody to get seated. We have limited number of rooms, as you can see. Okay. I'm assuming everything else is clear. Okay, so this is the agenda for the second part of the lecture. So we'll start with what we will learn, and then we will talk briefly about FPGAs, which will be the platform we will be using for the labs, and yeah, I will talk about the rest later. So you have seen this transformation hierarchy a few times by now. In the labs, what we will do is we will mainly get hands-on experience working on these 3 layers of this transformation hierarchy. So we will work at the software-hardware interface, microarchitecture, and at the logic level a little bit. Yeah, and then we will see how we can implement things at those 3 levels. Okay, so considering the trade-offs between performance and area complexity in your hardware implementation, so this will be, well, maybe not the most important part of your design. So mostly you will try to make something that works as described in the manual that we will give you. But in some parts, we will ask you specifically to satisfy some timing. So meaning your design should be able to run at some specific speed. Okay, so basically you'll get hands-on experience on hardware prototyping on FPGAs, debugging your hardware implementation. So as you end up with problems when you write a software program, the same happens on hardware, and then you will learn how to find the issues, how to find bugs in your hardware and fix those. And you'll also learn about hardware description languages, which are the programming languages people do to describe hardware. And we will also learn the hardware design flow, meaning from this high-level language or from the problem, starting from the problem definition, how you go all the way down to some specific FPGA implementation and get help to solve your problem. And we will be using computer-aided design tools or CAD tools to make some of the steps in this hardware design flow easier. So we won't be doing everything manually. Okay, so let me give you some motivation about FPGAs and where they are used today. So FPGA is basically a piece of hardware, a chip that can be programmed, not in the way that CPUs are programmed. So you don't develop a software program and then load it into your CPU, but instead you are directly modifying the hardware in some manner. Okay, and then hopefully it will be clear later in the slides. So I will show you some examples of how FPGAs works and how they're designed and how you can actually dynamically change the hardware. So let me first show you where those FPGAs are used today in today's system. So Project Brainwave is a Microsoft deep learning platform, and they use it for real-time AI inference and training. So FPGAs here help basically to do this AI training and inference very fast and in an energy-efficient manner. So yeah, as you see, the FPGAs here are very critical to achieve those goals. So Amazon is also offering EC2 F1 instances, which are basically server machines that have FPGAs that you can program and use in your applications. FPGAs are also today used in DNA sequencing machines. So those are basically machines that can read out your DNA and figure out what is the sequence in your DNA. And FPGAs are basically used in this kind of machines to accelerate many of processes that take a very long time. So here's an example paper which is proposing a mechanism to accelerate a specific part of this DNA sequencing process. So you can take a look if you're interested. And FPGAs are also used in in experimental DRAM studies. So here, this platform called SoftMC is using an FPGA to implement a custom memory controller that enables like accessing memory in a like very flexible manner. So at the programmer level in a CPU, you have, let's say, like a load store interface, right? So the instructions you are dealing with to access the memory are load store, but this kind of infrastructure enables more flexible interface to the DRAM where you can enable experimental studies. So one example is using this platform, you can like measure what is the retention time of the cells of your DRAM. So a similar infrastructure also exists to characterize flash memories, similar to DRAM. And you hopefully know about like flash memories as well. They have like they are being like widely used in SSDs today. Okay, so we will continue with the overview of the lab exercises. So what we will be doing during those 10 weeks. But before that, I would like to show you the FPGA board that we will be using. Okay, the most difficult part here is finding my mouse. Okay, so this here, this die here in the center of this board is the FPGA actually. So like we don't call this board an FPGA, so FPGA is the chip itself, so this is what we program. But the things that build on this board around this FPGA chip are mainly interfaces that we use to communicate with other devices. So I will be showing you a demo today where we will connect a keyboard to this FPGA and get the information about which key is pressed on this keyboard to the laptop that I have here. So basically, this is just to a toy example to demonstrate you that you can interface different devices using the FPGAs. So here in this FPGA, let me highlight you some things that we have on this board. So we have a USB. So you can basically design a hardware that will interface with pretty much any device that's compatible with this USB interface. You can get an VGA output from this device, so you can like present something on the screen, potentially. So there's a micro USB port on this. So this is what's used for programming the FPGA and for supplying power to the FPGA. So there's a power switch. So there are some other I/O devices on this board. So one of them is the 7-segment display. So this is just like to represent mostly some numeric values. So we have some labs that will make use of the 7-segment display here. There are also some other LEDs on this board. So those are also like the simplest like sort of output you can get from this FPGA. So basically driving one of those wires that are connected to the LED will make the LED glow. So I think sometimes this will be very useful for you for some debugging purposes. And we have some switches over here which we can use for binary input. Also some push buttons. And finally, we have highlighted the FPGA chip over here. Okay, so this will be FPGA board we will be using. And during the first sessions of the labs, we will be distributing a board to each group. So you'll be using one FPGA, like every 2 students will be using one FPGA. Okay. Are there any questions before I continue with the 10 weeks of the labs? Yes, please. So the board is called a Basis 3, as you see in the title of this slide. So I think it's about like 150 Swiss francs. But yeah, maybe you can find a cheaper one on the market. But there exists also different kind of boards that will be cheaper. You don't necessarily have to use this one, but we will be using this one in the class. Okay. Yes? No, you cannot. I had it here, but so yeah, don't worry about that. I think you can just try pretty much anything. So if you think like you are connecting like 2 wires together, that seems to be like short creating a short circuit, that I think it's not possible to cause any problem by programming. Yeah. So at least it's not a easy task. But of course, be careful with the FPGA. So some parts of it especially might be very sensitive to physical damage. So especially the switches. So don't be, don't push them too hard. Be careful with the board itself. Okay, so what's the goal of those labs? So at the end of the exercises, at the end of those 10 weeks or 10 labs, hopefully you'll have enough understanding to build a 32-bit microprocessor that will do some, maybe not a general purpose core that we have in modern systems today, but something that will enable you to run some simple applications at least. And we'll build this basically by the during those 10 weeks. So each week we will be working on a new exercise, except the last 2 weeks, I think. And not all exercises will require an FPGA board. So the first exercise won't require an FPGA. Instead, we will be just drawing circuits on the paper. Yeah, and you are encouraged to experiment with the board on your own. So as we already said, you cannot destroy it by programming. So I will do a demo today, so you can, once you get the FPGA, you can go and try the same thing yourself, or you can try other examples that are on the internet. Okay, so during lab 1, we will be drawing a basic circuit. So this is just for you to practice a little bit with the simple operations or simple gates that we have in hardware. Okay, let me display the entire thing. So what we'll be doing here is we will basically implement a comparator, right? So we'll be given 2 values. Here you'll be designing a circuit that will tell whether those 2 values are equal or whether one is bigger than the other. So that will be the goal of this one. So during the second lab, we will be mapping, we'll actually start working with the FPGAs, and then we will be implementing another simple operation, addition, in the FPGA. And then first we will design a circuit that will add 2 1-bit numbers. So if you add 2 1-bit numbers, the output will be 2 bits. And reuse this 1-bit adder to design a 4-bit adder. Okay, so this is called a modular design or hierarchical design, where we reuse some smaller building blocks to build something more complex and bigger. Okay, during the third lab, we will be using the 7-segment display, which I've shown you. So this is basically, you have, as the name suggests, you have 7 LEDs here that you can make them glow to represent different numbers here, or different letters even. So we will be using this to map the output of the 4-bit adder that you will design in the previous lab to display the numerical values here. But in that lab, we will be displaying the output just using the LEDs. Okay, during lab 4, we will move to something called finite state machines. So you will learn about this more during the class, but basically those are structures that have some memory. Okay, so far, before lab 4, all things you will be implementing will be called combinational circuits. So the output is only based on the inputs, right? But here, with finite state machines, we will start designing circuits that have some memory. Okay. And in lab 5, we will start implementing our simple processor. So we will be designing an arithmetic and logic unit called ALU for it. So the ALU is basically a unit that can do addition, subtraction, multiplication, comparison, and other operations. So we'll have lab 6 on testing our design, on simulating our design. So we'll learn how to debug the design and how to like simulate it to see potential problems. In lab 7, we will move to a slightly higher level of abstraction, and we will be working with assembly language, which is like, so we will basically write a program using MIPS instructions. So this is a particular ISA like x86 that Intel uses in their processors. So using MIPS, we will be writing some simple programs. And those programs will be running on the processor that you will be designing in lab 6 and lab 5. Okay, and finally, in lab 8, we will do full system integration, where we will be putting together all the things we implemented the previous weeks. And implement a simple snake program. You probably played different variations of this, so you'll be able to play this game on this 7-segment display on the board. And in the final, yeah, I think this is the final lab. In lab 9, you'll be learning how to measure the performance of your processor and even to like design some or make some additions, some changes on it to improve its performance. So mainly here you'll be implementing multiplication and bit shifting. So those will be 2 new instructions added to your processor to implement those operations. Okay, but before that, for the multiplication purpose, for example, to do multiplication, you'll be using like different operations, right? So like you can do addition, you can use addition to do multiplication with multiple iterations. So instead of that, we will be implementing a multiplier unit to make the processor do multiplication faster. Okay, so let's talk a little bit about what is an FPGA, and I will show you some details of like how FPGAs might be working today. But before that, any questions about the labs? Okay. Okay, so as I showed you previously, so this is the FPGA that we'll be using. So let's look at the FPGA chip itself rather than focusing on the entire board. So FPGA stands for Field Programmable Gate Array. So it just means that you can program it on the fly. So rather than just like program it after manufacturing or like having a fixed design that you manufacture and cannot change. So you can program this like multiple times and pretty much whenever you want. So it's a reconfigurable substrate. It has some units that we here refer to as reconfigurable functions. It also has a reconfigurable interconnect between those functions, so you can connect those functional blocks to each other in different ways. And this is very important for designing very big circuits, very complex circuits that will not fit inside a single function unit. So I will show you more concrete examples about this. And obviously this FPGA chip will also have some input output, so we can like interact with it and get some output and supply some inputs. So FPGAs basically fill the gap between software and hardware because they are more flexible than processors, but they also can be modified to some extent. Okay, so you can potentially use FPGAs in places where you want to interface some custom devices, right? So for example, you can just have a like device that you can not directly plug to your processor because it has like fixed like set of inputs and fixed set of devices that can interface. But using FPGAs, you can basically develop your own hardware solution very quickly and yeah, and have it implemented for like a very low cost compared to like designing an ASIC, designing an actual chip and getting it fabbed. And achieves higher performance than software. So those are the advantages of the FPGAs and has more flexibility than hardware. Okay, so in this slide, we will see some details about the internals of the FPGAs. So basically, there are 2 main building blocks of those FPGAs. The lookup tables, which we referred as functional units in the previous slide. So those will be the structures that we will we use in FPGAs to implement some functions, and switches, which determine how those lookup tables are connected to each other. So this is how a very small FPGA would look like. So here, each of those blue boxes is an LUT, a lookup table, and then we have like a bunch of other wires around them, and these circles represent the switches that are configurable that you can use to like connect the inputs and outputs of multiple LUTs in different ways. So when we look at an entire FPGA, the majority of the FPGA consists of interconnects, as you see over there, and lookup tables, essential. And lookup table is, well, I think there is a nicer picture showing that. So this is a typical 3-bit input lookup table here, and the yellow boxes on the left-hand side represent basically 1-bit memories. And essentially, when we talk about like programming an FPGA, what we're programming in the LUTs is those memories, those small memories. So depending on what values you write to those yellow boxes, you can implement a different function of this on this FPGA. And this lookup table has a multiplexer. So you remember multiplexers from the DRAM, where we show like when we access the row buffer, different portions of the row buffer, we multiplex multiple signals to access only like one of those 3 signals. So multiplexer basically works with, so here in this example, we supply 3-bit input to this multiplexer, as you see down here. And then this 3 bits determine which of these 8 bits to read and to output from this 1-bit output on the right-hand side of the multiplexer. Okay, so this is a multiplexer, and then this is the data input. This is what we call select input, which selects one of the data inputs. And so let's assume that we want to implement a simple logic operation like AND or NOT, right? So what this input is doing is, as I said, it is like helping you select one of those memory bits here. So when you supply 3 zeros from this input, this yellow box at the top, or its data, is being read, right? So similarly, to read other cells here, what you do is just supplying a different 3-bit input. Basically, 3-bit input can be used to implement any 3-bit function. So, do I have an example? Okay, so yeah. So here's an example of programming the ALUT. So let's implement a function that outputs 1 when there are more than 1 ones in the input, right? So yeah, so here, those are basically the addresses, right, for those yellow boxes. And we would like to output 1 whenever there are 2 ones in this address here. And it's pretty easy, right, programming such a simple circuit. What we need to do is just configuring these yellow boxes to contain these values. So whenever we see like 2 ones in the address or more than 2 ones in the address, we have to configure that corresponding cell with 1. So similarly, you can implement different functions here, right? So for example, you can do AND reduction or OR reduction. So AND reduction will mean within those 3-bit inputs, whenever we have a 0, the output will be 0, right? Otherwise, it will be 1. It's just simply the AND operation. Or you can implement an OR operation. Whenever we have 1, the output will be 1. Yeah, is it clear that you can implement like any function that has 3-bit inputs and 1-bit output? Okay. But how do we implement more complex functions that like do more sophisticated things? So as we said previously, FPGAs are composed of many LUTs and many switches. So we don't have to use a single lookup table to like implement the entire circuitry. But instead, we have to use many of those LUT and interconnect them in a specific way such that they solve the problem we want to solve. Okay, so like an actual FPGA chip would look something like this. So it's very dense. It's packed with thousands of lookup tables, and they are not they are configurable. Their interconnects are configurable in some way. So designing a very big circuit that will like make use of like those thousands of LUTs, and will need a very like very strict configuration of the switches is not an easy task. So doing it manually is not feasible, and this is why we will be using some tools to do those things. But let me, before like programming actual FPGAs and showing you how we program them, let me show you how a modern FPGA looks like. So typically they don't use 3-bit LUTs, but they use 6-bit LUTs, and they have like a bunch of on-chip memory and some special hardware blocks to interface main memory, like DRAM, for example, and do some other low latency and high bandwidth I/O. So here's an example of a like very high-end Xilinx, an FPGA from a company called Xilinx. So this is also the company that manufactures the FPGAs that are on our boards. So you can take a look at this. So basically the advantage of FPGA is that it has very low development costs compared to implementing some circuits on silicon and like getting them fabbed. So it's very short time to market. They are configurable on field. So if you figure out that you make a mistake in your design, you can go and reprogram your device. They're reusable, but disadvantages are that they are not as fast as ASICs. And reconfigurability actually adds some area overhead. So if you are designing at some fixed circuit, you can like pack everything together in a much smaller area than your FPGA chip, potentially. Okay, so for programming an FPGA, we will be using CAD tools. So those will like help us a lot with like different tabs in the design flow, because like programming FPGAs is difficult, especially if you want to map very complex functions to it. So this is a typical design flow. We start with the problem definition, and then we translate that problem to a hardware description language, and logic synthesis, placement, and routing happen. So those will be automatically performed by the software that we will be using. And finally, bitstream generation is performed to generate some sort of binary, which we can directly load into the FPGA. Okay, so for those, we will be using SilenceAvada, which you will find installed in the labs, but you can download it and install it on your laptop as well. It should be free. So you'll find some details about this in the first manual about how to install it, how to get it. So we don't have much time, so you can just look at this yourself, but this like briefly describes the tool that we're using. It's called LEVEDO, and as I said, it's installed on those rooms. And let me quickly show you the demo where we, as I said, we will be interfacing a keyboard. It will be a very simple project here that I will be showing you. So here I've opened a terminal, and then we will connect the FPGA to this terminal. So it will be using a serial interface. It's very slow, but it's like easy to implement in this case, and we don't need a very high throughput for this application. So whenever I press a key, first that information will go to the FPGA, and the FPGA will communicate that through the serial interface to my laptop here, and that value will hopefully be displayed on this terminal. Okay, so this is how LEVEDO looks like. Again, we'll have like more detailed tutorials in the manuals we will display, but you can also refer to this video later. So here, let's create one project. So I will just quickly continue those parts. So this is important. So in this screen here, we have to choose the FPGA that we are working with. So you don't have to memorize this right now. It will be all like given to you in the manual, but this is the particular FPGA chip that we are using, or that we have in this FPGA. Okay, so I create the project by selecting that particular FPGA, and then so here we actually start developing our hardware, right? But so I won't be writing a code here, but instead just add the source files of an existing project. So the link for this project was on the slides, so you can go and check it yourself later. So I'm just adding all those sources here. So those are source files for the design, for the actual design. So those describe the hardware that we want to implement. But there's also another set of source files called constraint files. And these source files basically map the input and outputs of our design to different parts of this FPGA board. So basically the constraints determine, like let's say you have a 1-bit output in your hardware, to which part of this FPGA will be connected to, right? So whether it will be connected to the 7-segment display or one of the LEDs or to some other interface on the FPGA. So after loading all the sources here, I will go through synthesis and implementation. So those are steps that the software will be doing for us. So this is similar to the process that the compilers are doing, right? So this is basically getting our program or hardware description written in HDL and translating it to some low-level details, right? That can be used to program the FPGA. So this takes a lot of time. Not for this particular application, which is quite small. I think it will finish within 10 or 15 seconds. But if you design a very big hardware that will probably fill the entire FPGA we have here, then it will probably take several minutes to complete all those steps here. And if you have even bigger designs, then it will take even more time. And the most time-consuming part in the design flow is actually what we call placement and routing. So placement is determining in which functional units and which switches to use on the FPGA. So because FPGA just is a sea of different lookup tables and the different switches, right? So it's very important to pick the right lookup tables and switches to find the most efficient design, right? The design that will work fast and will be energy efficient. So for example, if you pick 2 lookup tables that are quite far from each other, probably this will have a very high routing cost, right? And it will take more time basically for your signals to propagate, as a result making your circuits operate slower. Yeah, and after placement, the second step, routing, is basically about determining how those picked lookup tables will be interconnected to each other. So there are usually multiple paths. So I just click generate bitstream after this point, which will generate a file that I can directly download to the FPGA. Yeah, so routing is basically determining how to interconnect those selected lookup tables, and that is also a very time-consuming task. Okay, so now I will connect this FPGA to my laptop. And I guess there's not much to see on my screen right now, so I will switch to the DocuCam to show you the FPGA. So after connecting it here and turning on the power switch, so it started doing something. So this is the default program that is getting loaded to the FPGA every time. So this is basically an example program that tests all the I/O on this board. So here what happens is when the switches in this up position here, basically the LED glows, and otherwise it does not glow. Okay, so this is just a simple program that you can use to test all the switches and all the I/O devices on your board. So now I'm opening the hardware manager on my machine. You cannot see that, but it's not important. As I said, those will be on the lab manual, so there will be screenshots that will guide you through those steps. So now I will put the program. Okay, so it failed. Connecting. Okay, so the first step here is basically to connect your FPGA to this machine for programming, which is failing right now. Okay, but after this step, you are basically programming the FPGA. So right now I'm getting this error which says the port is like being used by other application. So you'll be also getting similar issues in the labs, and hopefully the TAs in the labs will help you solve these issues. And yeah, this was pretty much all for this lecture. We will have you, we will release a short video for this tutorial part, so you can watch it later. But basically, you can also go to the website and download this example and do the tutorial yourself. Okay, thank you.